Hello. This is Concrete Path. Today's lecture is saying that let's go get the problems of stress transformation and Mohrs circle. So your problem one, let's take the problem number one. You have a state of stress on plane P and plane Q. Let's say you have compressive 200 megapascal in sigma x direction, and you have a shear stress that's negative tau xy equals to 200 megapascal, and you got a sigma y equals to 400 megapascal. So you need to get the location of principal planes, location of shear stress plane, tau max plane, and you need to get the values of principal stresses and maximum shear stress. So let's go get those stresses. If we solve by analytical method, we would use the equations. Let's say sigma 1 or sigma 2 equals to sigma x plus sigma y by 2 plus minus sigma x minus sigma y by 2 whole square plus tau xy whole square. So sigma x is your minus 200 plus sigma y is your 400 divided by 2 plus minus that sigma x minus sigma y. Sigma x minus sigma y by 2 whole square plus tau xy. Tau xy is your negative 200 megapascal. So you solve that, you have 100 plus minus 360.555. So this part, that's your tau max. So we can say this is your tau max also. So let's get those stresses. That is major principal stress equals to 460.555, and minor principal stress, that is negative 260.555. So we got these. Now we would calculate where is the location of that principal planes. So for that we have the equation that tan 2 theta principal equals to 2 tau xy by sigma x minus sigma y. So you got a theta p, that theta p equals to 16.84 degrees, or we can say if you add plus 90, you get a value of 106.84 degrees. So now we want to cross check that on which particular plane, on which particular theta p you have sigma 1 acting, and on what theta p your sigma 2 is acting. So we would check now that. Let's check it for theta p equals to 16.84. So we would write cross check, right, at theta p equals to 16.84 degrees. We would write sigma x dash, that we had derived the equation. We call is that sigma x dash equals to sigma x plus sigma y, sigma x plus sigma y. Yeah, sigma x is 200, sigma x is minus 200, sigma y is plus 400. Sigma x plus sigma y by 2 plus sigma x minus sigma y by 2 cos 2 theta p plus tau xy. Value of tau is equals to minus 200 tau xy sine 2 theta p. So you got a value of minus 260.555. That's similar to what we got. So we got the sigma 2 equals to minus 260.55. That's minor principal stress. So at an angle of, so we can write that So at the rate of theta p equals to 16.84, let's make an angle of 16.84 with respect to the vertical plane. So this is our theta p. So on that particular plane, your sigma x dash is acting. That was, we calculated, equals to minus 260.55. That's also equals to sigma 2. So if you have that stress element on that, this is the notation that sigma x is acting, that's compressive negative, and on the other side it would be in this fashion, and perpendicular to this plane there would be major principal stress acting. So we'll write that major principal stress sigma 1 here. That value was 460.55. 460.555. So this is our two major principal planes, or we can say two principal stresses. So this plane is making an angle of 106.84 with respect to the vertical plane. So you have this plane with respect to this vertical plane. Your sigma 1 is making an angle of, sigma 1 plane is making an angle of 106.84. We can say in this fashion that this theta p, we can write this one as theta p1, this as theta p2. So this value equals to 106.84 degrees. Now the tau max plane would be at 45 between these two planes. If the angle between the two planes is 90 degrees, so the tau max plane would be at an angle of 45. So here somewhere. So this would be our tau max plane. So from this diagram also we can show that this is our tau max plane. So we can write here tau max plane. This is our tau max plane. We want to find we got the tau max value of that minus 260.844. Yeah, minus 360 point. That we have the equation that C plus R, C plus minus R, C was equals to 100 and R was equals to minus 3, that plus 360.555. So we got the tau max, but we don't know where it is locating, in which direction it's acting. So in the derivation we say this one is positive. So let's calculate. Now we want to cross check that at theta p, at theta shear equals to, we know that theta shear would be equals to theta p2 plus 45 degrees. Can we say, see, we have two shear planes, tau max planes. It can make an angle of 45 plus theta p2, or it can make an angle of we can also say this is also tau max plane. This one, it's making an angle of 45 with respect to the theta p1, or it's making an angle of we can say this is also making an angle of, say, somewhat in this fashion, that this is also making an angle of 135, and similarly this one, this is 45. So we can have four possibilities. With it can be negative, positive angle. So let's take the angle that with respect to the, so we will take with respect to vertical plane in anti-clockwise direction, theta s equals to this one. So we know that this was 16.84, and you substitute the value, you get theta s equals to 61.84 degrees. So let's calculate now the tau max equation that we have, tau xy. So you substitute these values and you get a value of tau xy dash equals to plus. So we got a positive. Now we want to calculate the sigma associated, that normal stress associated with the tau max plane. That we have that sigma x plus sigma y by 2. That sigma x plus sigma y by 2. That is we can say that that's the center. This is also the center. If you substitute the value, sigma x was your minus 200. Sigma x was minus 200. That sigma x was minus 200. Sigma x was minus 200 plus that sigma y was positive 400 divided by 2. That we get a value equals to 100 megapascal. That's always positive. So you can show that also here, that you have also a sigma x acting. This is sigma x. That sigma, it can sigma equals to 100 megapascal. So this is the stress representation. So if you want to make it by Mohrs cycle, let's draw Mohrs cycle. So let's say this is our reference origin. This is origin, and we got firstly we can calculate center. Center we have calculated that sigma x plus sigma y by 2. Sigma x plus sigma y by 2, that equals to 100. So add let's say this is 100 comma 0. Radius we know, radius we calculated as 360.555. So 360.555, let's make an angle of that 360.55, that circle. This is radius, so it will be somewhat in this way. So this is our circle. Now we want to plot the P plane and Q plane. So P plane, this is our P plane. So P plane is this one. On that you have compressive minus 200 megapascal and shear stress. Shear stress is in this fashion. So clockwise, positive tau. So we are right. So minus 200 and positive tau. So let's say this is minus 200 somewhere. Minus 200 comma tau. The value of tau shear stress was 200 also. So this is plane P. This point represents plane P, and now we have plane Q. This is plane Q. So on that you have sigma y acting tensile and a shear stress. Yeah, shear stress is acting in this fashion. That shear stress. This is shear stress. Actually the shear stress is this one. This is about this plane. We have shear stress of clockwise. Yeah. Now we want to say what's about this one. So this one is anti-clockwise. We can write that positive sigma y minus tau. Positive sigma y minus tau. So somewhere it would be at an angle of 180 with respect to the plane P. So this is that point Q, that plane Q. So this is the point plane Q. We can have here, we can write here that sigma y comma, yeah, we can write directly the values. So at plane A, we have principal stress major 1, sigma 1, and we have at plane B, we have minor principal stress sigma 2. So with respect to the vertical plane P, you have to make an angle of twice theta P to get the value location of principal plane 1, major principal plane. So this is our 2 theta P1. 2 theta P1, and this one we can say this one is 2 theta P2, 2 theta P2, 2 theta P2, 2 theta P2, yeah. And if you want to locate the tau max plane would be at an angle of, we have that equation that 2 theta s equals to 90 degrees plus 2 theta p. So if you want to get 2 theta s1, you can get 90 plus 2 theta p1. So you have to add 90s. So we can add 90 and you can reach somewhere here. So this is our 2 theta s. So right here. So this is our tau max plane. So this is point S1, and this is point S2. So this is tau max plane 1. Here the value was equals to minus that plus 360.555. That's also equals to radius. So we got this value. And similarly, if you want to find what's the value of theta S2, theta S2 would be at an angle of 2 theta P2 plus 90 degrees, somewhere here. So we have one more problem, that a point on elastic material is provided that we have the stresses, we have sigma x plus 40, sigma y minus, sigma y is positive 60, and shear stress, that's positive shear stress tau. The shear stress value equals to it's saying get the value of shear stress, how much tau we can allow, how much shear stress we can allow on this particular plane P and Q. So if the sigma max, if the maximum normal stress allowed is equals to 75 megapascal tensile. So you have to get the value of sigma, that tau value on which sigma max is 75 megapascal. So we can substitute the value of sigma 1 equals to sigma max 75 megapascal. So we got a shear stress value, that tau xy equals to, you calculate that value equals to, that value comes out to be equals to 41.53 megapascal. So your shear stress allowed should be less than this one, that should be less than this one, that should be less than tau xy, this 41.53 megapascal. So if you want to say why, let's have Mohrs circle. So we have center equals to 60 plus minus 40 divided by 2, that's 10. So 10 is somewhere here. So this is center, and radius value equals to, now we don't know the value of radius, but one thing is that radius value we don't know, but one thing is that we have sigma 1 equals to 75. We have sigma 1 equals to 75. So sigma 1 would be at 75 from here, 75. That means this value, we know that sigma 1 equals to C plus R. Do we know that? Sigma 1 equals to C plus R. If this one is C and this one is R, and we get a value of sigma 1 here on the plane A, so we can say, so your radius tau max equals to, tau max value we can get, initially we can get tau max value. So tau max value R equals to sigma x minus sigma y by 2 whole square plus tau xy whole square. So we got the value of radius, that's tau max. Tau max value comes out to be equals to, we have this 75 minus 10. So we have 75 minus 10. So 65 is the tau max. Tau max is 65. Yeah. Tau max is 65 megapascal. So you need to get what's the value of tau xy that can be allowed on this plane P and Q. So tau max is acting on some other plane A, but we need to get the tau at location on this plane P and Q. So we have to locate now the two planes P and Q. So we have sigma positive and tau negative. So 40 he is somewhere here. 40 comma tau value of 40 comma tau. 40 comma minus tau, and opposite that there would be yeah, it's compressive, that's negative, minus 40 comma tau, minus 40 comma tau, yeah, minus 40 comma, yeah, sigma is also negative, tau is also anti-clockwise, so both are negative, minus 40 comma minus tau, minus 40 comma minus tau. So this is plane P, this point represents plane P, and after that you have plane Q making an angle of 180 with respect to this plane. So there is somewhere here, it is somewhere here, plane Q. So plane Q is here. So here the coordinates are, this is your plane Q. Sigma x, sigma y is acting positive tensile, and a shear stress that is clockwise positive. So we have 60 comma tau. Now we want to say what's the value of tau at this location. So this is plane P, this is plane P. So if you got the value of that principal plane location, if you got the value of 2 theta p, yeah, if you get the value of 2 theta p, you can say what's this angle. Then if you get this angle, you can calculate what's the tau here value here. What is the tau value here? So tan 2 you can write tan 2 theta p. You can write tan 2 theta p. Tan 2 theta p equals to 2 tau xy by sigma x minus sigma y. But the thing is that you don't know the value of tau xy. You don't know the value of tau xy. Yeah. We can keep it as it is now. We can keep it as it is now. Yeah. So we have solved it by analytical method, and by Mohrs cycle shown the representation of those principal planes and your given planes P and Q, and how you can calculate that theta s. If you get this value of, let's say this is some theta, you can write that this is tau, and this is radius r, this is some sigma dash, and this is tau. We can write theta, we can write cos theta, sin theta. Sin theta equals to tau xy by radius we know. You can get the value of tau xy. Firstly, you have to get the value of theta p, theta here. So for that, you need to get the value of tan 2 theta p. Tan 2 theta p. Yeah. Tan 2 theta p. Let's take one more. Let's take one more problem. So you need to get the normal, tangential, and resultant stresses. On you have a 20-degree plane. You have a plane that's making 20 degrees with respect to the vertical, or we can say major principal plane. With respect to the major principal plane, your desired plane is making an angle of 20 degrees. So if you have stress element and the sigma is acting here, sigma x, is positive 80 and sigma y is 40. And there's no shear stress acting on these planes P and Q. So we can say out of these, the major principal plane would be on which major principal stress is acting. So this plane, this is our major principal plane. So with respect to this plane, this is our vertical plane. So with respect to this, you have to make an angle of 20 degrees. You are making an angle of you have to make an angle of 20 degrees with respect to this principal plane. So on this desired plane, you have to get the values of sigma value, tau value, and some resultant values, sigma resultant. So we have those equations. We can write that sigma x dash equals to sigma x plus sigma y by 2, sigma x plus sigma y by 2 plus sigma x minus sigma y by 2 cos 2 theta, cos 2 into 20, cos 2 theta, and plus tau value is 0, because these two values are principal planes, principal stresses, because no shear stress is acting on these planes P and Q. So we can say these two values are principal stresses. So your tau value is equals to 0, and you get a value of sigma x dash that comes out to be equals to sigma x dash comes out to be equals to sigma x dash 75.32. Let me check it one more time. 60 plus 20 cos 2 theta. Yeah, we got this one, and so we got a positive value. That means the direction would be in this fashion. So this is our sigma x dash 75.32, and now we want to calculate tau xy dash. So tau xy dash equals to minus times sigma x minus sigma y, by 2 sine 2 theta, sine 2 into 20 plus tau value equals to 0. So that term goes to 0, and we can get the value of tau xy dash, that is equals to 12.86 40 sine 12.86, and this is negative. This value is negative. Negative means the direction would be upwards. So shear stress would be upwards. So you need to get now we got the two values, that normal stress we got, tangential stress we got, sigma x dash, tau xy dash, and you need to get the stress resultant stress on that particular plane. So the resultant stress value equals to sigma resultant equals to tau xy dash square plus sigma x dash square. So this is the sigma resultant on that particular plane. So you have some stress. One stress is acting in this direction, this one is acting in this direction. So we can get the stress resultant, this equation we have, and we substitute the values, and you get a value of stress resultant that comes out to be equals to 76.41 megapascal. Now there is one more point, that how much theta it's making. So you have this sigma x with respect to the sigma x, or we can say normal to the surface, normal to the plane. If this is our plane, desired plane, normal to this plane, if what's the angle that the stress resultant stress is making. So we can say if this was your plane P, if this was plane P, if you draw normal to it, what's the angle that your stress resultant stress is making with respect to that normal? That we call as alpha. So that's called as angle of obliquity. So we write that angle of obliquity. So it's alpha, angle between, it is the theta between the normal to the surface, normal to plane, and stress result and resultant stress uh, on that plane. So we got the values that we got a tau xy paused upwards, tau xy, and the resultant would be somewhere in this direction now, sigma resultant. So this is our alpha. Can we write this equation? So this is our tau xy, this is tau xy. So we made a triangle, and we can write that tan alpha equals to perpendicular by base. So we can get the value of alpha now. So value that alpha equals to, we got a value of that alpha equals to 9.686 degrees. So we got the alpha. Now we got this alpha is that it is theta with respect to sigma x. We can say normal to plane 20 degrees, that normal to plane 20 degrees. So this is if we see that the direction of the theta, that's we can say this is the theta. Why it's, yeah. So this is downwards. Once you got the sigma x direction, then after that you have sigma x downwards. So if you plot it on this stress element, so this was our stress element, that so this on the stress element, this is the sigma x, and your stress resultant got in this fashion. So the resultant stress is making an angle of, with respect to the principal plane, with respect to the plane P, it's making an angle of, we can say 20 minus alpha. Can you say that? See, total angle was 20. Total angle was 20. Total angle was 20, and stress resultant makes angle of 20 minus alpha with respect to vertical. The value comes out to be equals to 10. I think we should wind up this class now.